Good evening, gentlemen. Welcome back to the old computer shack. Today, I want to talk about this memory card I've been working on, this PDP-11 QBus memory card. I ended up, I've almost got the layout finished on it. It's not the greatest layout ever, but it's getting close to being done, and I'll move this down when I get to connecting the bus here. I mean all of this stuff so the bus traces aren't great big and long. I just had it up here so I had room to fart around with it, right? But anyway, it's a thing, you know. It's got jumpers on it to use it with 64 kilobytes of RAM for like a LSI 11.2 or 11.3, or 256K of RAM for like an older 1123 that doesn't have a memory management unit, or 22 bits, 4 megabytes for an 1123 with an MMU, or an 1173 or better, or whatever. And it uses static RAMs, and you can configure it to ignore any RAM below a certain base address, so you can use like your vintage cards that you've got, and then use this to fill in the rest of your memory map. Was the idea. However, I think I'm gonna, even though it's almost done, I ended up buying a couple of 2 megabyte ClearPoint RAM cards from a gentleman on the Vintage Computer Federation forum, so I'm going to put this on the back burner for the moment and continue with the H11 using those cards. But we will get back to this later when I try to get the 1123 working in that extra backplane that I've got, because we'll need a RAM card for it. So we'll finish this then. But first, I want to get the H11 going first. But I figured, just to, top this off and get it out of the way, I'd go through and try to describe how it works. So here over on this side we have a couple of 74 LS640 inverting bus transceivers, and these are just like an LS245, except the outputs are inverted. Well, it inverts whatever goes through it, whatever direction it's pointing in, because the QBus is inverted. I guess it was cheaper to do it that way back in the day, but in any case, these act as bus transceivers. They buffer the signals off of the bus into the rest of the card. And then we've got these two 8-bit latches on the other side of the bus transceivers, because the QBus uses the same lines, these same data and address lines, for both address and data. So what it does first is it the bus master, typically the CPU, but it could be like a DMA device, but the bus master typically puts the address that it wants to fuck with on the bus, and then it asserts this sync signal that comes in down here somewhere, B-sync, yeah, and gets inverted, turned back into like an active high signal here through this LS240 down here. But anyway, the sync signal is what latches the address onto these two 8-bit registers here, right? And so then these remember the address that's been pointed to, so that the address decoding remains valid once the data is put onto the system bus over here. So this garbage over here deals with the address decoding. And basically it just takes the most significant two address lines and puts them through these two to 4 decoders and turns them into chip enables for the memory chips that we'll look at here in a little bit. And there's some extra stuff in here so that all of the decoding can be inhibited by this inhibit line. That's for when the I/O page is being accessed, or when the address that's being decoded is lower than the configured base address that the card responds to. And there's some stuff for doing 8-bit writes instead of 16-bit writes and stuff in here. In any case, this is what generates the output enable and write enable signals off of the D in and D out signals on the QBus and other such things. So anyway, after a certain amount of time, after sync has latched this data onto has latched the address into these latches, it places the data on the bus, the same bus, and asserts either D in or D out, depending on whether it's a read or a write. And that signal is what tells the RAM to latch the data that's being presented on the data bus here into its internal memory. And then we generate a delay here with this RC circuit, and it gets combined with the sync signal, and after a certain delay, it asserts this B reply signal on the system bus, which signals the CPU that the data has either been written into the RAM or if the bus master is reading data from the RAM, it means that the RAM is placing data on the bus and the data is valid. And this has to be an open collector signal, and I didn't want to waste a whole IC just on one open collector inverter, so I'm faking it with a transistor there. That's what an open collector inverter looks like inside of an IC. So we're just using a 2N3904 bipolar junction transistor there. I think it's beefy enough for our purposes. It could easily be replaced with a transistor with a larger current sinking capability if necessary, but that should be fine. It's kind of a cheesy way to do it, but I was trying to be cheap. Anyway, yeah, then if we go into the RAM here, these are the RAM chips. There's nothing unusual there other than on bank 0, so that we can support the AS6C 1008 and the AS6C whatever the hell it is, 65256 or whatever the 32K by 8 one is. This jumper replaces A16 or pin 30 on our IC socket with 5 volts, which is necessary for the 1008 and the whatever the fuck the 32-bit chip is. 32K chip, I mean. So if we go back up here, wait a minute, we have to look at so this is bank 0, and you can see that there's an extra thing here. The 32K chip is shorter, so it just would install, 2 of them would install in the bottom part of these 2 sockets. The 1008, that's for setting up a 256K 18-bit card. It's the same size as the 4008, so they just fill up the whole socket, but you have to set this jumper because it needs 5 volts on pin 30 as a chip enable rather than A16, and of course the 256 has VCC on that pin, so it ends up serving the same purpose for those 2 ICs. But the 4008 has VCC up here and address lines here, so that jumper changes that. And then for a 22-bit card, we could populate as many of these pairs as we wanted to. We could either do 1, 2, 3, or 4 megabytes, depending on how many chips we put into it, pretty much. So, yeah. What are we forgetting about here? That's really about it. The base address of the card is determined by this comparator down here. So you set these jumpers to whatever the maximum base address that the card will respond to is going to be, and it just asserts this inhibit line if the actual address is lower than that. It only works within the lower 512K because we've only got 8 lines to compare here. But that's fine, and it takes the IO segment into account too when it asserts this inhibit line. So that's how that works, and yeah, that's really all there is to it. It's not nearly as complicated as it seems when you first start reading the QBus specification. Now, one thing that's been brought to my attention, this LS640 is not an open collector bus driver, and the original digital chips, the DS, they were originally a TI chip, and then DEC started having them marked as DEC or something like that. The original the bus drivers that DEC used were open collector bus drivers, and these are not. The Heathkit memory cards that I've got, they use LS240s as bus drivers, which are also not open collector bus drivers. And for something like this B-reply line, which could probably not, but maybe theoretically be asserted by more than one card at a time, or especially for like interrupt requests and DMA requests and stuff like that, you've got to have an open collector driver on those, or everything gets jacked up. But for the data bus, for asserting data on the data bus, we can kind of cheat. I think this will work. It may not be stable in like a great big system with multiple backplanes connected with a bunch of like long ribbon cables and shit like that, like they used to do. But for like a hobbyist system in a single backplane, I think this will work all right. And I guess if it doesn't, we can jump off that bridge when we come to it. The proper open collector bus drivers are ridiculously expensive now. So we're just kind of faking it there. And I guess that's really all there is to this. I just wanted to make a video right quick because it's been a while. I've been kind of distracted with this and busy with other things, but this was nice and quick and easy to do, so I'll post this, and then the next video will be about trying to get the correct power good signals generated the old-fashioned way with RC circuits and Schmidt trigger buffers, so that we can power up the extra backplane using a PC power supply and test our Q-bone, and then start testing our cards without risking the actual H11. The H11 probably be fine. I don't think we're going to blow up the power supply, but regardless, it's big and it won't be very convenient on the bench. So we'll test the Q-bone on all the cards in the extra backplane, assuming we can get these signals to happen. So anyway, that's the next thing. Thank you for joining me. I'll see you all next time.